Chemical properties of alkynes. There are specific headings, so you need to remember these headings so that you can recall later on. Acidic character of alkynes we will be talking about under chemical properties. Then we will be talking about addition reactions, and within addition reactions there will be 5 major types: addition of dihydrogen, addition of halogens, addition of hydrogen halides, addition of water, and polymerization. Within polymerization, we will be talking about 2 types of polymerization. The first one, linear polymerization, the other one, cyclic polymerization. First, acidic character of alkynes. This one is specifically important because a few questions normally appear that which one will be more acidic, which one will have higher electronegative character, okay, which one will be more basic. Arrange these in decreasing order of acidic character or basic character, like that. So most of those questions will have one specific reason which we are going to talk about. There might be other reasons as well, so one of those reasons I will be talking about here in acidic character of alkyne. Here, reason for acidic nature is, we know that S character, we talked about S character, which obviously depends on the hybridization. So here both the carbons are sp hybridized. This is sp hybridized, this is sp hybridized. It means S character is 50%, 50% S character here, 50% S character on the other carbon. And the rule is, the higher the S character, higher the electronegativity, higher the acidic character. I will tell you why. Okay. Higher the acidic character, because in alkenes you have sp2 hybridized. In alkenes, sp2 hybridized carbon, so S character is only 33.3%. In alkanes we have sp3 hybridized, means S character is just 25%. Means alkynes have maximum S character out of these 3. So that's why these are most acidic out of these 3. Why? Understand it one by one. The reasons: 50% S character, sp hybridized. It means carbon atoms have highest electronegativity. When I am saying highest electronegativity, I am comparing it with alkenes and alkanes. With compared to that one, highest electronegativity. It means, as per the definition of electronegativity, it will attract the shared electron pair with a greater force. So here what will happen here, in CH bond, the carbon will pull the shared electron pair towards itself because it is highly electronegative in comparison to alkenes and alkanes. Otherwise it will not be very electronegative. So when it pulls the electron pair towards itself, hydrogen will get partial positive charge. Similarly here, hydrogen will get partial positive charge. And what does it indicate? The partial positive charge means it can now be released as proton more easily. It has got positive charge. It has got positive charge as compared to alkenes and alkanes. So it means it can easily be converted to proton, and that is the definition of acid. Acids give proton. So for example, HCl is acid. It will give you H plus. So it gives you proton. If you have H2SO4, that is acid, it will give you H plus and HSO4 minus. It will give you a proton. So the compounds which can give proton, which can release proton, are acids. Here ethyne has, or alkynes have, higher tendency to lose proton. So that's why they are more acidic as compared to alkenes and alkanes. So hydrogen atom can be liberated as proton more easily, acidic nature. I would suggest you write all these points, all these 5 points in the order, so that you are able to answer these type of questions. Questions are really easy. Most of the students are not able to answer these type of questions because they are not able to relate these concepts with the question. These are the examples. So ethyne, here when reacted with sodium, hydrogen is liberated, half H2. So what happens? Sodium here replaces hydrogen. Here again sodium reacts and it replaces the other hydrogen as well. So here I am calling it monosodium ethanide because I have just one sodium. Here I am calling it disodium ethynide because I have both the hydrogens replaced by sodium. Another example, here you have propine, okay, and you get it reacted with NaNH2. Again sodium will replace this hydrogen. This carbon now does not have any hydrogen to be replaced, so only one replacement will be there. So there is no need to say monosodium propionide. We just need to say sodium propionide. There is no possibility of having disodium propionide. Now there is something specific which you might have noted. The point here is that the triple bond must be at the corner. In such cases, the triple bond must be at the corner. Only in those cases, the alkynes will show the acidic nature. Why? Because suppose I consider this one, CH3C, triple bond C, CH3. Now both of these carbons do not have any hydrogen attached to these. These both are attached with carbon. So there is no possibility, even if I get it reacted with sodium, there is no possibility that sodium can replace the hydrogen from the triply bonded carbons. It means this will be least acidic. Okay, so this one will be most acidic. Why? Because it has two hydrogens. Ethyne has two hydrogens which can be replaced. Propine, it has just one hydrogen which can be replaced. Butene has no hydrogens to be replaced, so least acidic. So if you are asked to arrange these in decreasing order of acidic character, it will be ethyne, propine and butene if all are alkynes. However, if you have to compare alkynes, alkenes and alkanes, in that case alkynes will be most acidic, alkenes will be less, and then alkanes least. So these reactions are not shown by alkanes and alkenes, and the reason is very simple, because their hydrogen is not replaced by sodium. Hence these can be used for distinction between terminal alkynes and alkanes or alkenes. Remember, I am saying terminal alkynes because if it is not terminal alkyne means the triple bond is at the corner. The triple bond is at the corner. Means butene is not a terminal alkyne because the triple bond is in the middle, not at the corner. So we can distinguish between terminal alkynes and alkanes or alkenes. So if you have been given, for example, ethyne and ethene, you can use this distinction. Ethyne will give this reaction, ethene will not give you. Or ethyne and ethane. Okay. Similarly, propine and propene, or propine and propane. Propine will give this reaction, propene and propane will not. Okay. And you can also use this to distinguish terminal and non-terminal alkynes. So within alkynes also you can distinguish if one alkyne is terminal, the other one is non-terminal. So this test is also used to distinguish between terminal alkynes and non-terminal alkynes. So for example, butene and butene. So butene will be CH3CH2C triple bond CH, and butene will be CH3C triple bond C CH3. Here hydrogen can be replaced because hydrogen is at the terminal. Carbon has hydrogen, the triply bonded carbon has hydrogen. Here no triply bonded carbon has hydrogen, so the reaction will not be shown. Rate of reactivity of alkanes, alkenes and alkynes will be in this order. Means alkynes will be most reactive, alkenes will be less, alkanes will be least. And the reason is very simple, because here you can replace the hydrogen very easily because of high electronegativity of carbon, because it has 50% S character. So it has 50% S character. So it will pull the shared electron pair towards itself with great extent. Here carbon has 33.3% as character. Here it has only 25% as character. So that's why the hydrogen cannot be released very easily from here. The carbon will not pull the shared electron pair with great force in case of alkanes. Then rate of reactivity of terminal and non-terminal alkynes. Again, it is very easy to understand. Here you have two hydrogens which can be replaced by sodium. In this case, you have only one, and here you have none. So obviously, it will be the decreasing order. Rate of reactivity. Now we will be talking about the addition reactions one by one. First, addition of dihydrogen. It is Sabatier and Sanderens reduction, which we have talked about in alkenes also, and in preparation of alkanes also. In preparation of alkanes and in properties of alkenes we have talked about. So ethine, when reacted with hydrogen in presence of catalyst platinum, palladium or nickel, will give you ethene, and ethene will further react with hydrogen. Again, Sabatier and Sanderens reduction will continue, and finally we will get ethane here. If we have propine, again similar reaction will be happening. We will first get propene, and then propene will get converted to propane. So in all such cases, ultimate product will always be alkanes. Okay, addition of dihydrogen will lead to alkanes, whether it is alkene or whether it is alkyne, final product will be same. Addition of halogens, when we get alkynes reacted with bromine or chlorine, okay, we get vicinal halide alkenes. Okay, then this further reacts with bromine, and again the next pi bond breaks and the bromines get attached. So it is actually now tetrabromo, 1122 tetrabromo propane. Addition of hydrogen halides, it is similar to the Markovnikov addition, though here it is not called Markovnikov addition, but it is similar to that one. So suppose this is the one, this is symmetrical alkyne. So if it is symmetrical alkyne, bromine can go to any carbon, hydrogen can go to any carbon. Okay. Now here you need to understand why the next bromine gets attached to same carbon. The reason is very simple. As per Markovnikov addition, now if we get it reacted with HBr, bromine will go to that carbon which has less number of hydrogen atoms, and this carbon has only one hydrogen, this carbon has two hydrogens. So obviously Br will go to that carbon which has less number of hydrogen atoms. So that's why you have Br2 here. So this is the way to remember. If it is reaction with HBr, it will be as per Markovnikov addition. Okay, if it is with Br2, bromine, chlorine, then vicinal dihalides, vicinal tetrahalides will be produced. Okay, so I'm going back just to tell you what is the difference when we get it reacted with halogens. Halogens are symmetrical. Okay, so because these are symmetrical, we can't say one bromine will be more positive, the other one will be more negative. Both are same. So they will get attached to both the carbons, 1 each. Okay, and then again 1 each. These are symmetrical molecules, bromine, but HBr is not symmetrical molecule. Bromine is negative part, hydrogen is positive part. So here Markovnikov addition will take place, and that's the reason you will get gem dihalide. This is called gem dihalide. When the halogens, both the halogens are attached to same carbon, we call this as geminal or gem dihalide. Now this one, suppose you have propine. Here you know where the bromine will go. In case of ethine, it was symmetrical alkyne. But here you know the carbon, this carbon has no hydrogen attached, means it has less number of hydrogen attached. This one has one. So you won't consider this one. This carbon has no hydrogen, means less number of hydrogen atoms, means bromine will get attached to this carbon. And then again when the reaction takes place, now double bond, the carbon which has less number of hydrogen atom, again same. So further addition of bromine will take place on the same carbon. Again you will get geminal dihalide. Geminal dihalide means the halogens are on the same carbon, 2,2-dibromopropane. So if these reactions happen to appear in your exam, you should be able to write if you remember the rule. Addition of water, again very similar to what we did in case of HBr. Water, instead of HBr, water is HOH. So instead of Br, you will consider OH, and it will be same thing. OH will get attached to that carbon. This is negative part. Negative part will get attached to that carbon of alkyne or alkene, which has less number of hydrogen atoms. So OH got attached to any carbon here because it is symmetrical. Next, what happens? Isomerization takes place. Now, isomerization basically what does? It moves the hydrogen from here to here. Now, in case of isomerization, where hydrogen moves from one atom to another atom, this type of isomerism is known as tautomerism. Tautomerism. Tautomerism is that isomerism when hydrogen atom moves from one atom to another one. Another one normally is carbon. Okay. This is called tautomerism. And we actually get here carbonyl group, and it is ethanol in this case because here you have hydrogen. It can be ketone. This is carbonyl group. It can be ketone if we have the methyl group here, ethyl group here, any alkyl group. So next example is that one. So in this case, if it is ethine, it will give you ethanol. All other alkynes will give you ketones. So this is again the case. OH will go to which carbon? OH will go to that carbon which has fewer number of hydrogen atoms. Again, tautomerism will happen and you will get ketone. Only ethine will give you ethanol, that is aldehyde. All other alkynes will give you ketones. You need to remember this reaction takes place with HgSO4 and H2SO4. You might get it written as Hg2 plus H2SO4. So there are various possibilities. You can get it written like HgSO4, H2SO4. Temperature obviously needs to be same, 333 Kelvin. You can get it written as Hg2 plus and H2SO4. You can get it written as HgSO4 H plus. Various ways. Okay. But it is same reaction we are talking about. Then the last one, polymerization, linear polymerization and cyclic polymerization. The linear polymerization is very simple. You have monomers, multiple units of monomers, and they form the polymers. Okay, so here you see that two molecules get attached to form one polymer molecule. So you can say that if you have 2n molecules of this one, you will get n times here, right? Under special conditions, these polymer conduct electricity also. Thin film of polyacetylene can be used as electrodes in batteries. These are the usage of the polymers being produced here after linear polymerization. These films are good conductors, lighter and cheaper than metal conductors. So in places where we can't have heavy metals, okay, we need lighter parts, there these polymers are used to conduct the electricity or to be used as electrodes. Cyclic polymerization, this is something you have done earlier also in case of general organic chemistry, that when ethine, 3 molecules of ethine combine, when they are passed through red hot iron tube at 873 Kelvin, they combine to form benzene. This is a specific example of conversion from aliphatic compound to aromatic compound. So this is also known as aromatization. Aromatization. Non-aromatic compound, that's aliphatic compound, gets converted to aromatic compound.